to the lecture series on differential equations for undergraduate students. Today's lecture is on Fourier series. In series solution of differential equations, we had learned many series such as the Taylor series and Taylor polynomials. There we had learned that if we have to approximate the solution at one point, we can use the Taylor series or Taylor polynomials. Or in other words, we had learned that Taylor polynomials can approximate the function locally, but not globally. That is, if we have to approximate the function at a particular point, say for example, if we have to find out the limit, we can use the Taylor series. But if suppose we have to approximate the integral of a function over an interval, then of course this Taylor polynomials or Taylor series, they cannot give the answer. Then what to do? The answer comes in the form of Fourier series found by J.B. Fourier in the development of the theory of heat conduction. Later on it has been found out that the series which he has found out, that is a very important mathematical tool in solving many other engineering and application problems. Thus, these series have been named after his name and they have been called the Fourier series. So, now let us try to find out what is the Fourier series. Fourier series is a series of cosine and sine terms. This arises basically in a study of periodic phenomena, or in other words we can say the Fourier series are obtained for the periodic functions. What are periodic functions? A function f(x) is called periodic if it is defined for all real x and if there is some positive number p such that f(x) plus p is f(x) for all x, that is, it is repeating itself after some time, and this number p is called the period of f(x). Say for example, in this particular function we see that the function is from 0 to 4, it is a triangle, and then again it is repeating in the same one. Or if we just go like this one, this is what is the periodic function with period as 4. Similarly, let us see this another function. Here if we try to see from 0 to 2 and then from 2 to 4, again we are having is the function is moving like this one, and after that it starts repeating itself. That is, if I take value at 0, that is same as value at 4. If I take value at 1, this is same as value at 5. So, again it is a periodic function. This is also another example of a periodic function. Here is one more example of periodic function. You see here is that the period, you do find it out that the function is started from 0, it has gone up to 6 and then again it is started repeating. So, now we find out that the period is 6. This is again one more periodic function. Now, we had seen that f(x) plus p is equal to f(x). This is what is we are defining as a periodic function. This says is if I take f(x) plus 2p, this would be f of x plus p and plus p, that we can write it as f(x) plus p by the first equation, which is same as f(x). What it says is that f(x) plus 2p is also same as f(x). Moreover, if we just go on like this one, then for any integer n we can get that f(x) plus np would be f(x) for all x. So, what it says is, now I do have a function which is defined for all real number x such that f(x) plus p is f(x), f(x) plus 2p is f(x) and f(x) plus np is same as f(x) for any integer n. That says is my p, 2p or np all are periods. So, we can say this function to be periodic with period p or 2p or np. So, all these are period of the function. If a periodic function f(x) has a smallest period p, then this p is called the fundamental period of f(x). So, we had seen that if it is a period p, then 2p, np, all those would be the periods. So, what we would call, we just call this p, that is smallest integer, as the fundamental period, and normally we just name is that this period rather than using the fundamental period, we just simply say period. So, let us see in our examples. this was one periodic function. If we see, the function is repeating after 4. So, we have started from minus 3 to minus 1 to plus 1. So, minus 3 to 1 you see is the function is same. Then it has started repeating again, it has come. If I try to see this whole lot, that is from here to here, and again if I try to see, again it is or rather if we just go with up to here, and then if we see is again my function is repeating. So, either I could say the period is from minus 3 to 1, that is the 4, or from minus 3 to 5, sorry, it should be till here 5. So, what we are getting is that either we could say is that the period is this much or the period is this much, but the fundamental period where this is smallest one where it starts repeating is this one, that is from minus 3 to 1. Similarly, let us see in this one here also, we find it out that it starts repeating after this time. So, this is the smallest value, that is 6, after which it starts repeating. So, we just get that the 6 is the fundamental period for this function. We have this trigonometric functions, as we said is that sine and cosine functions, we have defined the Fourier series. So, we see that the sine function, this has a period 2 pi, because 0 to pi it is a positive curve and then it is coming as negative. So, 0 to 2 pi, after that it starts repeating itself. Similarly, for the cos pi, if I see, again we could say either from minus pi to plus pi or then minus pi to plus pi and then pi to 2 pi. So, we just find it out, that is the function is repeating from here to here, and so we just simply say that the period of the sin x and cosine x, they are 2 pi. So, sin x has the fundamental period 2 pi, that says simply that sin x plus 2 and pi x is sin x for all x. This we do know already from the trigonometry. And similarly, for cosine function also, that is cosine of x plus 2 and pi x is equal to cos x for all x. One more result for this periodic function, that is if f x and g x are two functions of period p, then if I take a function h x defined as a linear combination of f x and g x, that is a of f x plus b of g x, this will also be a periodic function and will have the period same as p, where this a and b are some constants. Say for example, if we could see here, if I have taken the sin x and cosine x, both are periodic function with fundamental period p. So, if I take sin x plus cosine x, we find it out that this is again your function with period 2 pi. So, this is the graph of sin x plus cosine x. Now, trigonometric functions will just come up. Some trigonometric functions with period 2 pi, they are sin x, cosine x, sin 2x, cosine 2x, sin 3x, cosine 3x and so on. Let us see their graphs. Here is the function sin x and sin 2x. This white line, this is sin x function, its period is 2 pi. So, let us say 0 to 2 pi from here to here. Then this colored line, this is sin 2x. We see is again it is also repeating after 2 pi, but we see here the fundamental period for sin 2 pi would be actually sin 2x would be actually pi. You see it is repeating after here itself, but of course, as we say is that if p is the period, 2p and np, they all of them can be called as period. So, here we say is that sin x has the period 2 pi, sin 2x also has the period 2 pi. Similarly, for the cosine x, we do have is that cosine x you do have the period from 0 to 2 pi and then again cosine 2x, this is cosine 2x is this white line. So, you are finding it out again, it is repeating after pi, but we could just go ahead with till pi and we are finding it out that this is also of 2 pi. So, we can say that is sin x, cosine x, sin 2x, cosine 2x and so on, they would be all of the period 2 pi. So, if I take this series a naught plus a1 cosine x plus b1 sin x plus a2 cosine 2x plus b2 sin 2x and so on. Here cosine x, sin x, cosine 2x, sin 2x, all these have period 2 pi. A naught is a constant function we can have with any period. So, we can say is that period 2 pi again. So, we do have this is a linear combination of the functions with the period 2 pi. So, this series would be actually a function with period 2 pi. So, this trigonometric series we could say is a function with period 2 pi, where all these a naught, a1, b1, b2 they are real constants and they are called the coefficients. We can rewrite this series as a naught plus summation n is running from 1 to infinity a n cos n x plus b n sin n x. Now, what we are getting is 1 sin x, cosine x, sin 2x, cosine 2x and so on. These we would be calling the trigonometric system. So, now we have just formulated the terms before going for the Fourier series. Fourier series we said is a series of containing the terms of sin x and cosine x. Here we have taken a trigonometric series which is containing cosine x and sin x terms, and moreover we had also learned one thing is about that the periodic functions, and we had find out that the sin x, cosine x all of them are periodic functions. So, this series we could treat as a function with period 2 pi. This basic functions 1 sin x, cosine x and so on, this system we would call trigonometric system. Now, come to the Fourier series. How do we find out the Fourier coefficients? What we are saying is that is the trigonometric series which we had find out, we said is that is it is containing the function. So, this complete series can be taken as a periodic function with period 2 pi. So, the question comes only, that is if any function which is of period p or period 2 pi, that can be approximated by that trigonometric series. Only thing is we have to find out what are those coefficients a naught, a1, a2, b1, b2 and so on. How to find it out? Let us see. First we are assuming that f x be a function of period 2 pi and this is integral over its period. Whenever it is having a period 2 pi, normally we write it out, that is it is from minus pi to plus pi rather than writing it from 0 to pi. This is convention, we can write anything, but normally we write minus pi to plus pi. Further assume that f x can be represented by trigonometric series as a naught plus summation n is running from 1 to infinity a n cos n x plus b n sin n x. Now, we integrate this function on the series on both the sides from minus pi to plus pi. So, we integrate it, this says is that I would get integral minus pi to plus pi f x dx is same as integral minus pi to plus pi a naught plus summation n is running from 1 to infinity a n cos n x plus b n sin n x dx. Now, integrate it out the right hand side. For integration we are assuming that f x is uniformly convergent on minus pi to plus pi, then this integral can be written the right hand side, we can write as the integral of some functions, I can write as sum of integral functions. These things you might have learned in some other courses, that is when we can integrate or the series and integration sign, that summation integration sign can be interchanged. So, like that if I am writing that it would be a naught minus pi to plus pi dx plus summation n is equal to 1 to infinity a n integral minus pi to plus pi cos n x dn x plus b n times minus pi to plus pi integral sin n x dx. That should be equal to 2 pi a naught. Why? Because integral minus pi to plus pi sin n x dx is 0 and integral minus 2 pi to plus pi cos n x dx is 0 for all n. So, what is being left is only the first term a naught minus pi to plus pi dx, its integral is x. So, from plus pi to minus pi, this is 2 pi. What it gave me? It gave me that integral minus pi to plus pi f x dx is 2 pi a naught, or in other words a naught is equal to 1 upon 2 pi minus pi to plus pi f x dx. So, the first coefficient a naught we had found out. Now, move for the other coefficients. So, for a n, what we will do? We will multiply with cos m x for some fixed integer m and integrate from minus pi to plus pi this whole series. That is, I will multiply both the sides with the cos m x here and here, this whole series, and then integrate over minus pi to plus pi. This says is left hand side minus pi to plus pi f x cos m x dx would be same as minus pi to plus pi integral a naught cos summation of n running from 1 to infinity a n cos n x plus b n sin n x into cos m x dx. Now, again we will assume that uniform continuity and convergence, and that this series summation and this integral sign, they can be interchanged. That will give me this minus pi to plus pi f x cos m x dx as a naught integral minus pi to plus pi cos m x dx plus summation n is running from 1 to infinity a n integral minus pi to plus pi cos n x cos m x dx plus b n integral minus pi to plus pi sin n x cos n x dx. Now, integrate it. The first term, just now we had seen that in the last integral, that integral minus to pi to plus pi cos m x dx is 0 for all integer m. So, this will be 0, and then we have integral cos n x cos m x sin n x and cos n x. This integral will come as a m times pi y. Let us see, we have to integrate one by one these integrals. So, let us see first this integral cos n x cos m x. This integral, this function cos n x cos m x we can write as half of cos m plus n x plus cos of m minus n x dx. And now, this m plus n and m minus n both are integers. M plus n is an integer, m minus n would be integer, but it would be 0 if m is same as n. And then what we are getting is that if m is not equal to n, I would get this integral as some cos p say kx and some cos lx, both are integers, and we already know that integral minus pi to plus pi cos n x is 0 for all integer n. If m is equal to n, in that case it would be, this part would be 0 of course, but here what we would get? We would get cos 0. Cos 0 is 1. So, what we will get? Integral minus pi to plus pi 1 dx, and that would be 2 pi, half into 2 pi, that would give me pi. So, we are getting is that this first integral would be pi if m is same as n. Moreover, this integral you could see that is it would be 0. So, now come up to this second integral sin n x cos m x dx. This we could write as sin n plus m x plus sin n minus m x dx. Now, this is again sin k x and this is sin l x when n is not equal to m, and we already know that integral minus pi to plus pi sin n x dx is 0 for all integer n. When n is equal to m, this is some integer, but this would be 0 and sin 0 is 0. So, again this whole function would be 0 for all m and n. That is why the second part of the integral will not be contributing anything, and what we have got the result, we have got that a m is equal to 1 upon pi minus pi to plus pi f x cos m x dx. This is true for all m 1, 2, 3 and so on. Now, move to find out b n. For finding out b n, what we will do? We will multiply with sin m x, this series f x a naught plus summation running from n is equal to 1 to infinity a n cos n x plus b n sin n x, and integrate it on complete interval minus pi to plus pi. So, what we would get, that left hand side integral minus pi to plus pi f(x) sin mx dx, and right hand side as minus pi to plus pi a naught plus summation running from 1 to infinity a n cos nx plus b n sin nx multiplied with sin mx dx. Again we will assume that the uniform convergence and this summation sign and the integral sign can be interchanged. So, I would get it first term a naught sin mx dx, that is 0, integral minus pi to plus pi. Second term, second we would be getting is a n times integral minus pi to plus pi cos nx into sin mx dx, and that in the previous integral we have just find it out that there it was cos sin mx and cos mx, that is n and m were interchanged, that is all, but that does not make any difference, that was 0 for all n and m. So, the first integral, that is the coefficients a n's, that is whatever we are getting, that integral would be 0. Another integral would be b n as sin nx into sin mx, and that is pi b m. Why? Because we could see is that the second integral sin nx into sin mx, that can be written as cos m plus nx minus cos m minus nx, like that, and that again would be pi only when m is equal to n, and that is what we are getting here, it is pi b m. Thus, we are getting it that b m is equal to 1 upon pi integral minus pi to plus pi f(x) sin mx dx for all m 1 2 and so on. So, we see is that is, as earlier we have shown that cos nx sin mx dx is 0 for all m and n, and this sin mx sin nx, that can be written as half times minus pi to plus pi integral cos n minus mx plus cos n plus mx dx, and that would be 0 if n is not equal to m, and if n is equal to m, that would be pi. So, we have got the coefficients, these coefficients we call that Euler's formula for Fourier coefficients. What we had obtained? We had obtained that a naught is equal to 1 upon 2 pi minus pi to plus pi f(x) dx, a n is 1 upon pi minus pi to plus pi f(x) cos nx dx, and b n is 1 upon pi minus pi to plus pi f(x) sin nx dx, and this is true for all in 1 2 3 and so on. These are called the Euler's formula for Fourier coefficients. What are the Fourier coefficients? That is, if we do have any periodic function with period 2 pi, we can represent it as a trigonometric series containing a naught plus summation n is running from 1 to infinity a n cos nx plus b n sin nx kind of thing, and where this a naught, a n and b n we can obtain using this Euler's formula for the coefficients. So, the Fourier series of the periodic function f(x) is a naught plus summation n is running from 1 to infinity a n cos nx plus b n sin nx with Fourier coefficients a naught, a n and b n as obtained above. Now, let us try with example. Find the Fourier series of the function f(x) which is minus a in the interval minus pi to 0 and a in the interval 0 to pi, and it is periodic, that is f(x) plus 2 pi is equal to f(x). You have to find out the Fourier series of this function. Let us see how we are going to do. The Fourier series means we have to obtain a trigonometric series of the form a naught plus summation n is equal to 1 to infinity a n cos nx plus b n sin nx, and the Fourier coefficients will obtain by the Euler's formula. So, first for a naught 1 upon 2 pi minus pi to plus pi f(x) dx, f(x) is this above function. So, what we are finding it out, minus pi to 0 it is minus a and 0 to pi it is a dx. So, if I integrate over here, what I do get is minus a pi plus a pi, that is 0. So, a naught is 0. Now, let us come to the a n. A n is 1 upon pi minus pi to plus pi f(x) cos nx dx. My f(x) is minus a in minus pi to 0 and from 0 to pi it is a. So, we just write this integral as 1 upon pi integral minus pi to 0 as minus a times cos nx dx and 0 to pi as plus a times cos nx dx. Now, integrate it, we get minus a times sin nx upon n 0 to minus pi to 0 plus a times sin nx upon n from 0 to pi, and we do know that as x is equal to 0 sin 0 is 0 and at x is equal to pi whether plus or minus sin n pi is always 0. So, we are getting this is 0. So, we have got a naught is 0 as well as a n is 0 for all n. Now, let us come to the b n. b n is 1 upon pi minus pi to plus pi f x sin n x dx. Again we will put the value of f x, that is from minus pi to 0 it is minus a times sin n x dx plus integral 0 to pi a times sin n x dx. Now, if I integrate it, we do get it as 1 upon pi a times integral of sin n x is minus cosine n x upon n and minus a times cosine n x upon n 0 to pi. So, when x is 0, cos 0 is 1, when x is minus pi it is minus cos n pi, and when cos is plus pi, x is plus pi, it would be cos pi. So, we would be getting it as a upon n pi, cosine 0 minus cosine minus n pi minus cosine n pi plus cosine 0. Since cosine of minus x is same as cosine of x, we would be getting it as 1 minus cosine n pi and 2 as common, cos 0 is 1. So, what we are getting is for n odd, that means n is 1, 3 and 5 and so on, I would be getting it as cos pi by 2, that is cos n pi by 2 is 0. So, I would be getting it as 4a upon n pi and it will be 0 for n even. So, we would be getting it since cos 0 is 1 and cos n pi is minus 1 for n odd and plus 1 for n even. So, this is what we have got b n, that says is b n we have got as a naught is 0, a 1, a 2 is 0, b n is 4, b 1 is 4a upon pi, b 2 is 0, b 3 is 4a upon 3 pi and so on. Thus, the Fourier series we would obtain is 4a upon pi sin x plus 1 by 3 sin 3 x plus 1 by 5 sin 5 x. You see is that coefficients a naught, a 1 they are 0, we are getting just only the b n's, and that summation n is running from 1 to infinity, b n sin n x, that is n would be making it, b 1 is 4a upon pi, b 2 is 0. So, again we would be getting is 3 times. So, this is 4a upon 3. So, 4a upon pi we have taken common, sin x plus 1 upon 3 sin 3 x plus 1 upon 5 sin x sin 5 x and so on. Now, let us see is that is what we have obtained for this function. If I take only the first term S1, we call it 4a upon pi sin x. This is the first partial sum we are saying. S2 as 4a upon pi sin x plus 1 by 3 sin 3 x and so on, say let us say S3, till 3 terms we are just writing it over here. And let us try to see if I try to approximate the function by this Fourier series, let us see that is how it is approximating. Let us see by the graph. If I take only S1, this is the function minus a from you could say 0 to minus pi, it is minus a, and 0 to pi it is plus a. So, this is the periodic function you are getting is just this is square kind of function, square waves kind of function it is coming up. And if I approximate it by first partial sum, that is my only 4a upon pi sin x, we are getting this function. You see is that is we are approximating it. So, we are getting is that it is matching from this endpoints and all those things, but as we are approaching towards this upper ones, we are reaching above ones. Let us see if I use the first two functions, that is S2. Now, you see is that is we are first we are moving very far away, now we are coming little bit inside here. Let us see if I am just using the third function, that is S3. that is 3 terms we had used. Now we are approximating. So now if I am going on increasing my n, that is if I am approximating my function by this Fourier series, as I am increasing the number of terms in the approximation, I would be getting is that this function would be more near to this whatever the function, actual function we are getting. You see is that is here also we are matching too much. You see in the previous one also, first one you see we are deviating from here, then we have started matching it till here. So, little bit deviation over here, let us see this points, and then we have gone this third one, we find out that is we are not deviating, we are deviating only at this point, and then as we are going to increase the number of terms in this one, we would be more stabilizing, or we would be more correctly approximating this function over this whole interval, that is on the whole real line. Let us see one more example. Find the Fourier series of this function f x is equal to x from minus pi to plus pi, and its periodic, that is f x plus 2 pi is equal to f x. Since we have just obtained only to find out the Fourier series for the functions which has period 2 pi, so we are just taking those examples. So, let us see what we have to do. That simply says is we have to find out a series of this form a naught plus summation n is running from 1 to infinity a n cos n x plus b n sin n x, and this coefficients a naught, a n and b n we would be using by finding by using this Euler's formula. So, a naught is 1 upon 2 pi minus pi to plus pi f x dx. Since my function f x is x from minus pi to plus pi, we do find it out that f of minus x is same as f of x. So, we are minus of f of x. So, we are getting it as 0, it is an odd function. Moreover, when we come to this a n 1 upon pi minus pi to plus pi x sin f x sin n x dx, this is also 0, because minus pi to plus pi x sin n x dx is also 0. Since x cos n x is an odd function, that is f of minus x is minus of f of x. So, we have b n now 1 upon pi minus pi to plus pi x times sin n x dx. Now, integrated by term by parts. So, it is 1 upon pi, the integral of sin n x is minus cosine n x upon n, integrate from minus pi to plus pi evaluate, and then another integral plus 1 upon n minus pi to plus pi cosine n x dx, because the derivative of x is 1. Now, when I am keeping the values and evaluating it, I would be getting it as minus 1 upon n pi, pi cos n pi plus pi cosine n pi, that is the second integral as well, and this is minus 2 upon n cos n pi, which is 2 upon n minus 1 to the power n plus 1, because cos n pi is minus 1 to the power n, and 1 minus sign I have taken from here, that is this minus sign I have merged over here. So, what this is what we have got b n, which says is my b 1 would be 2, n is 1, b 2 would be 2 upon 2, that is and with the sign would be minus 1 to the power 3, that is minus, b 3 would be 2 by 3 with plus sign, and so on. So, what we will get the finally Fourier series a naught and a1 a n's we have got 0, and this 2 I have taken as common, first term sin n x minus second term with minus 1 by 2 sin 2 x plus sin 3 x with 1 by 3, and so on will go on, that is the next sign would be minus actually. So, this is what is my Fourier series. Now, again try to approximate it with the function in the graph we would see. So, for that let us first find out that the partial sums we are calling it, that is the first term, second term, that the sum up to first term, second term, and so on. So, this is what is my complete Fourier series, and the partial sums are S1 is 2 sin x, S2 is 2 times sin x minus sin 2 x by 2, S3 is 2 times sin x minus sin 2 x upon 2 plus sin 3 x upon 3, and so on like that. So, let us see in the graphs. You see here is in this graph actually this line which is being shown here is joining this one, that line is not there, this is just in the graph that this line is coming up here. We just have that this function is where we have marked once, this is not the line, this is just showing it up. And if I approximate this function by the first partial sum, you see our approximation is from here to here, it is coming up little bit, that is at the points where it is meeting with the x axis, at those points it is matching, but we are deviating from here, and because of this, that is what I have shown, that is the function, if I just draw this one, this function will be the straight lines, but if I try this function to be the continuous ones, because it is a piecewise continuous, here the function is discontinuous. So, if I try to join it, it would be like this one, but this is what it is, this Fourier series is also making it one, and that says is we are deviating from the function a little bit more. Now, let us move to the second partial sum. This second partial sum we are getting is that, of course, because of this discontinuity we are deviating, but now we are little bit more near, that is here we are trying to be more near to this one. As we move to the third partial sum, you see we are more near to the approximate values at the points over there. So, like that, if we just increase on, that is if by whole Fourier series I am approximating it, you see is now here on this line the points are decreasing. The line actually in the function, this is the point and this is the point, no other point in between. But if we see in the first partial sum, you see we are getting many points over here, but if I just come to the second partial sum, I am getting less points over here. When I am moving the third partial sum, I am getting again more less points. So, as we are increasing my n, that is the terms we would be actually approximating this function more nicely. So, you do find it out that the Fourier series in this one, only thing we require is that the function has to be continuous. It may be discontinuous, that is what we are calling piecewise continuous. We can approximate the function by the Fourier series. The function has to be periodic and the period is 2 pi. Now, it is not that is we do have only the functions of the period 2 pi only, we can have any period. So, can we find out the Fourier series for any period 2L? Now, we are just using it 2L. So, let us say f x is defined and integrable on the interval minus L to plus L, and f x plus 2L is f x, that is my period P is 2L. Then we try to find it out. Can we find out the Fourier series for this? We will just try to obtain it with the method, as we are seeing is we are approximating it with the series containing sin x and cosine x. Sin x and cosine x, they are periodic functions with period 2 pi. So, we will just try to find out the answer from there itself. So, let us say define a new variable pi x upon L, let us call it v. Now, if I take the function f x which is defined on minus L to plus L, now we would take the new function g v as f of pi x upon L. So, I am defining another function g for all x belonging to R. So, my original function, my f x is defined from minus L to plus L. Now, I have changed my variable to v as pi x upon L. So, what will happen, since x is in minus L to plus L, what I would get, that my new function g v, this would be actually from minus pi to plus pi. Since when x is minus L, I would get the value for v as minus pi, and when x is plus L, I would get the value for v as plus pi. So, now if I change the variable x to v, I would get the new function, and the new function I defined like this one, I would get the new function from minus pi to plus pi, and since I am defining it for all x and the original function f x is periodic with f x plus 2L is equal to f x, I would get g v plus 2 pi is equal to g v. So, now set g v as f of L v upon pi. Now, I am again rechanging it. Now, you see what it gives me, that now this new function this is now periodic with period 2 pi in the V. So, I can write it as A naught plus summation n is running from 1 to infinity a n cos n v plus b n sin n v. Now, rather than x I am using it v, and what I would get? I would get this function coefficients using the Euler's formula. So, x is L v upon pi, we get v as pi x upon L, and now what I am getting is g of pi x upon L, that is f x, which is, because finally I have to find out the Fourier series for f x. So, I am again rewriting it. I am getting it as a naught plus summation n is running from 1 to infinity a n cos, now n v I would write pi x upon L. So, n pi x upon L plus b n sin n pi x upon L. Now, this is what we have got, the Fourier series for function f x, where the period of function is 2L. And the Fourier coefficients with the Euler's formula, again we will just go back. A naught, now you see a naught from here, it should be, if g v is the function with the period 2 pi, and with any function with period 2 pi, we do know that a naught is integral minus pi to plus pi 1 upon 2 pi g v dv, that there it was f x dx. So, because we are changing it to x to v, this would be, now if I rewrite it, what I would get is, I would get it minus L to plus, because g v is same as f x, where g v is defined from minus pi to plus pi, f x is defined from minus L to plus L. So, I would get it, this is same as 1 upon 2 L minus L to plus L integral f x dx. Similarly, we would go with a n would be 1 upon pi minus pi to plus pi g v cos n v dv. Now, we would change to the x and we would get it as 1 upon L minus L to plus L integral f x cos n pi x over L dx, and this would be for all n 1, 2, 3 and so on, and b n we would be getting is 1 upon pi minus pi to plus pi g v sin n v dv, again changing it to the x, we would get 1 upon L minus L to plus L f x sin n pi x over L dx. Thus, what we have got, this is true for again for 1, 2, 3 and so on. So, now we have got Fourier series for any periodic function. The period could be any period p, which we are saying is equal to 2L. That is for our convenience, we are just writing it as 2L. That can be obtained using the Euler's formula. This new Euler's formula are now a naught is 1 upon 2L minus L to plus L f x dx, and a n is 1 upon L integral minus L to plus L f x cos n pi x over L dx, and b n is 1 upon L integral minus L to plus L f x sin n pi x over L dx. And now, the Fourier series we would be having is a naught plus summation n is running from 1 to infinity a n cos n pi x over L plus b n sin n pi x over L. So, now let us see one example over this. Find the Fourier series of the function f x, which is 0 from minus 2 to 0 and x from 0 to 2, and the period is 4, that is f x plus 4 is equal to f x. So, here my period p is 4, that says is L is 2, because we are taking as p is equal to 2L. So, now what we would get, L we have obtained as 2. Now, we will find out the Fourier series of this form a naught plus summation n is running from 1 to infinity a n cos n pi x by 2 plus b n sin n pi x by 2, because my L is now 2, and what a naught, a n and b n we will obtain using the Euler's formula. So, we have been given, this is the function, a naught is 1 upon 2L, that is 1 upon 4 minus 2 to plus 2 f x dx. f x is 0 from minus 2 to 0 and x from 0 to 2. So, we would get it as 1 by 4 0 to 2 x dx, and that would get x square by 2 and so on, integrated over this one and evaluated from 0 to 2, I would get it 4 by 2, that is 2, that is we would be getting it as 1 by 2. Now, a n 1 by L, that is 1 by 2 integral minus L to plus L, that is minus 2 to plus 2 fx into cos n pi x over L, that is L is 2 dx. Fx is 0 from minus 2 to 0. So, this integral would be half times integral 0 to 2 x times cos n pi x by 2 dx. Now, integrated by parts, we would get half as outside. This first x is as such, integral of cos n pi x by 2 is 2 upon n pi sin n pi by x, sin n pi x by 2 evaluated from 0 to 2 minus 2 upon n pi, this derivative of x is 1, 0 to 2 sin n pi x by 2 dx, which when I would be evaluating it at x is equal to 2, I would be getting it as sin n pi, that is 0. At x is equal to 0, this is 0 as well as sin 0 is 0. So, the first function would be, first term would be 0, and we would be getting it as minus 1 upon n pi 0 to 2 sin n pi x by 2 dx, which when again we would be integrating it, we would be getting is 2 upon n pi square cos n pi x by 2 0 to 2. At 2, I would be getting it as cos n pi, and at 0 I would be getting it as cos 0. So, this is 2 upon n pi square cos n pi minus 1, because cos 0 is 1. So, cos n pi is minus 1 to the power n. So, we are getting this 2 upon n pi square minus 1 to the power n minus 1, and Bn finally we would be getting it as 1 upon 2, that is 1 upon L, integral minus L to plus L, that is minus 2 to plus 2 fx sin n pi x by L, L is 2 dx. Function is 0 from minus 2 to 0. So, the integral would change to half times integral 0 to 2 x times sin n pi x by 2 dx. Again integrating it by parts, we do get it as minus x 2 upon n pi cos n pi x by 2 0 to 2 plus 2 upon n pi 0 to 2 integral cos n pi x by 2 dx. Now, here when we keep x is equal to 2, I would get cos n pi. When x is equal to 0, this 0 will give 0. So, we would be getting it as the first term as minus 2 upon n pi cos n pi, since 2 is here and 2 is here. So, it will be cancelling out, and this 2 and this 2 is again cancelling out. So, I would be getting is this integral as 2 upon n pi whole square sin n pi x by 2 evaluated at 0 to 2 pi. When x is equal to 2, I would get sin n pi, and when x is equal to 0, I will get sin 0, both are 0. So, that is not going to put any term over there. We would get it as 2 upon n pi minus cos n pi is minus 1 to the power n plus 2 upon n pi square sin n pi minus 0, both the terms will give me 0. So, finally, we are getting is 2 upon n pi minus 1 to the power n plus 1, that is minus sign here, it has been deleted little bit. So, we are getting it this minus 1 sign over here, that is minus 1 to the power n plus 1. So, the Fourier series would be fx as half plus summation n is running from 1 to infinity 2 upon n minus 1 to the power n minus 1 upon n square pi cos n pi x over 2 plus minus 1 to the power n plus 1 upon n sin n pi x over 2. Thus, we would be writing it out, that is expanding it, half minus 2 upon pi whole square, that is we are taking common, and we would be getting the terms here cos pi x upon 2 square plus cos 2 pi x upon 4 square plus and so on cos n pi x over upon 2 n whole square and so on, and then we would be getting the sign terms as 2 upon pi sin pi x by 2 upon 1 minus sin pi x by 2 minus sin 3 pi x by 2 upon 3 and so on. So, finally, we would get the here the general term as minus 1 to the power n plus 1 sin n pi x by 2 upon n and plus so on. So, we are getting this is the Fourier series of the function fx, which was having a period of period 4. It was not of the form 2 pi, but we could get it as here we are getting the sign terms as pi x and like this one. Let us see another example. Find the Fourier series of the rectangular wave, which is 0 from minus 2 to minus 1 and k from -1 to +1 and 0 from 1 to 2, and the period is again 4, f(x) plus 4 is f(x). So, we do have again a function of period 4. So, my p is 2l is 4, so l would be 2 again, and I want the Fourier series of this form. So, again here l is 2, so I would be getting is n pi x by 2. So, we would be getting we want a series of the form a naught plus summation n is running from 1 to infinity a n cos n pi x by 2 plus b n sin n pi x by 2. This a naught, a1, a n's and b n's will find out using the Euler's formula. This is my f x which is given to us. So, a naught 1 by 4 minus 2 to plus 2 f x dx. This is 0, function is 0 from -2 to -1 and 0 from 1 to 2. So, the function is only k from -1 to +1. So, we would be getting it as k by 2, this integral. Next, a n 1 by l, that is 1 by 2 minus 2 to plus 2 f x cos n pi x by 2 dx. Again the function is k only in -1 to +1. So, this integral would be k by 2 minus 1 to +1 cos n pi x by 2 dx. Now, integrate this function cos n pi x by 2, we do get is sin n pi x by 2 into 2 upon n pi. So, k by 2 into 2 upon n pi sin n pi x by 2 from -1 to +1. When I keep x is equal to +1, I would get sin n pi by 2, and when I keep x is equal to -1, I would get minus n pi by 2. So, the value for sin n pi by 2 is 1 and value for sin n minus n pi by 2 is -1. That will give me a n as 2k upon n pi into sin n pi by 2. Now, sin n pi by 2, that is when n is even, I would get it is of the form sin 2 m pi upon 2, that is sin m pi, that will always be 0. When it is odd with 1, 5, 9 so on, I would be getting it as a +1. So, this will be 2k upon n pi. When it is 3, 7, 11, I would be getting it as -1. So, it is minus 2k upon n pi. Because we do know that sin pi by 2 is +1, sin 3 pi by 2 is -1 and so on. So, we just find out that this is what the a n we had find it out. Now, b n 1 upon 2 minus 2 to plus 2 f x sin n pi x by 2 dx. Since the function is k only in the interval -1 to +1, I would get this integral as k by 2 minus 1 to +1 sin n pi x by 2 dx. Now, function sin x is odd function. So, -1 to +1, it will always be 0. So, what we have got? We have got that for rectangular wave function f x 0 to 0 between -2 to -1 and 1 to 2 and k from -1 to +1, the Fourier series is k by 2, this is a naught which we had find out, plus 2k upon pi cos pi x by 2 minus 1 by 3 cos 3 pi x by 2 and so on, plus 1 upon 5 cos 5 pi x by 2 and so on. This is what is the Fourier series for this function we have got. So, today we had learned what is Fourier series. We have learned that this is a series of sine and cosine functions, and it could be given as that a naught plus a1 cosine x plus a2 cosine 2x and so on, plus b1 sin x plus b2 sin 2x and so on, when the function was of the period 2 pi. We had also learned how to obtain for any function f x these coefficients a naught, a1, a2, b1, b2 so on, which we are calling Fourier coefficients. We had learned Euler's formula for that. This we have done for a periodic function with period 2 pi. Then we have moved to the any periodic function, that is the period is of any p, or rather we call it any 2l rather than 2 pi, and we had learned how to obtain the Fourier series for a periodic function with period 2L. Again we had modified our Euler's formula for finding out the Fourier coefficients and we had find it out. We had seen in the examples, we have done 2 examples for Fourier series for periodic functions with period 2 pi. There we had seen also in the graphs, that is how those functions, when we are approximating by the Fourier series, as we are moving towards many terms, we are obtaining that the functions are being approximated by those Fourier series, and we have learned for the other functions, periodic functions with period 2 pi. Next, some more properties of this Fourier series for this periodic functions we will learn in the next lecture. So, today's lecture is over here. Thank you.